We are the Yukon Senior Design Team undertaking the project of underwater data transfer. The sponsor for this project is General Dynamics Electric Boat. The focus of this project was the investigation into current technologies relating to wireless underwater data transfer. Our use case for this device is hopefully the development of a communication system between two moving underwater platforms. The deliverables from the electrical and engineering group is to provide a MATLAB Simulink model and a proof of concept for the hardware, while the computer science group will be providing the communication code and the mechanical group will be providing the waterproof design and thermal analysis.
There are a variety of technologies that are currently being experimented with in the realm of underwater communications. For this reason, our sponsor has provided us with a series of specifications that we would use to determine which technology is most appropriate. Currently, naval submarines use acoustic technology as their form of underwater wireless communication. Acoustic waves can travel extremely long distances, however, they suffer from limited maximum data rates and large power consumption. The main alternative to acoustic is RF communication, which has a significantly higher data rate, usually in the realm of megabit per second. The energy consumption scales with distance, usually at low milliwatts, around 3 meters between communicators. The main problem with RF communication is a high level of attenuation by water and the previously mentioned distance dependence.
For our project, we will be using optical communication, which has had the largest focus in recent years. Optical communication generally is understood as data transmission using light rather than sound or RF. Modern implementations of an underwater wireless optical communication system would use multiple lasers in a focused array targeted towards the receiver system. Gigabit per second data rates are also obtainable using optical communication, along with much more energy efficient signal transmission. This combined with the low attenuation by water would make optical communication a significantly better choice than RF.
Unfortunately, there are still downsides to underwater optical communication, such as a lack of commercially available completed systems to experiment with and test, as well as the high degree of complexity and cost. The current state-of-the-art research does not have a simple theoretical model for long-distance channel effects for underwater optical communication. There is also a significant line of sight restriction, which limits the ability to scale the system into something capable of high-performance use at this time. Now, we will walk through the 4 steps of electrical design and demonstration, starting with the system description and then ending with the physical proof of concept.
The structure of a simple underwater communication system starts with an input of data, either in an audio or serial text format. The data is then sent to a microcontroller, which will then modulate the data using a modulation scheme in what is essentially a digital to analog conversion. The data is modulated in a way that will allow a laser diode or diode array to vary its output intensity, sometimes with the help of a driver circuit. The laser output is then sent through the underwater channel and will reach the optical receiver, sometimes accompanied by an amplifier. The reading from the photodiode is then sent to the second microcontroller, which demodulates the signal and provides output data.
The Simulink model serves as a general skeleton of the system, which can later be expanded upon and refined. The current version of the model has a very simplified on-off keying transmitter and receiver, as well as a constant attenuation optical channel. Future iterations of the project can incorporate different encoding or modulation techniques, as well as a more sophisticated channel design as more optical channel research emerges.
The circuit diagram and physical concept were developed from our general understanding of simplified optical communication and existing physical designs using the same or similar components. Despite significant precedent regarding the use of lasers with Arduinos, there was not a lot of specific information regarding Arduino code for wireless communication, most likely due to the prevalence of error in the signals and the relatively low clock rate of the Arduino. This video demonstrates the proof of concept hardware design of a laser-based data transmission system. The red laser diode on the right Arduino is sending data to the optical receiver, which is wired to the filter circuit attached to the left Arduino. There is also an oscilloscope reading of the signal between the optical receiver and the leftmost Arduino.
Lastly, we will look at the mechanical requirements of the project along with the housing unit design and thermal analysis. For additional safety, a housing unit was designed to hold the communication system and be inserted into the UUV. It is required to be corrosion resistant and have the strength and heat transfer ability to maintain operating conditions of the data transfer equipment. For the housing unit, we designed it around the most durable geometry for pressure and the shape of the UUV being a cylinder. Waterproofing being an important part of the design, a 2O-ring acetal design was used to withstand higher pressure. A stress analysis was performed at 5 times the pressure at the max depth of the UUV itself, and the wall of the housing unit deformed about 1 millimeter and the cap deformed about 0.2 millimeters. The housing unit provides a 1 millimeter gap between the inner wall and communication system, and therefore we'll be putting pressure on the system due to this deformation. With this in mind, the system would be functional at 200 meters depth still. Finally, we performed a thermal analysis to study how the heat would disperse with the Arduino in the housing unit. The system was tested under stationary UUV conditions, experiencing convection on the outer wall of the UUV from water currents and a uniform heat flux from the Arduino. This analysis shows that the steady-state Arduino temperature is about 7 degrees above the ambient temperature across the entire range of the ambient operating temperatures. Therefore, this asphalt housing unit proved to fit the heat transfer needs of the underwater data transfer system. Here's the analysis in action at 0 degrees ambient temperature. This shows the system dissipating heat generated from the Arduino through the walls of the capsule in UUV. System equilibrium temperature is driven towards the ambient temperature, and the communication system consistently stays within 10 degrees of the ambient. In summary, not only is our design capable of withstanding pressure at depths of 200 meters, it was designed with a 5-times safety factor to ensure the safety of the electronics within. The design also allows for efficient heat transfer through the entire UUV system to ensure the communication system remains operational and does not overheat.